Hi, this lesson is about interference and path difference for coherent waves, and this will be in the context of the microwave oven. The animation here shows how a microwave oven works. The microwaves are produced by a magnetron inside the oven. They travel down a straight path to a stirrer which reflects them into the microwave oven. The microwaves are then reflected around the oven. The microwave oven heats by causing water molecules to oscillate incredibly fast to generate the heat. And that's the way cooking occurs in a microwave oven. The cooking in a microwave oven does not happen evenly, and that is why a microwave needs a turntable. This can be demonstrated by this network of LEDs that's been placed in the microwave oven. We'll see that there are hot spots and cold spots when the LEDs either light up or extinguish. The reason for these hot spots and cold spots is constructive and destructive interference that is being caused when waves that are reflecting from different parts of the microwaves are interacting, like so. And so if we were to place a tray of marshmallows, let's say at the bottom of the microwave, and we switch the turntable off, some of them would melt where there was maximum oscillation, like you can see here, and when there was zero oscillation occurring, the marshmallows would not melt. So we'd have hot spots and cold spots. This is how we'd explain constructive and destructive interference in terms of the phase of the waves interfering. For constructive interference, we know that the phase difference is 2n pi, where n is 0, 1, 2, 3, etc. For destructive interference, the phase difference would be n pi, where n is the odd numbers. In this slide, I'm going to explain complete constructive and destructive interference in terms of the path difference of the waves that are interacting. So first of all, constructive interference, and there would be a path difference of lambda as a minimum difference. We could also say that the path difference is n lambda, where n is 0, 1, 2, 3, etc. For complete destructive interference, the path difference, or the minimum path difference, would be a half lambda. Or as a series, we could say n plus a half lambda, where n is 0, 1, 2, 3, etc. Another factor that is also very important if we're going to have complete constructive interference or complete destructive interference is that the waves are coherent waves. Coherent waves are waves that have the same frequency and constant phase difference. So coherent waves can produce paths of complete destructive and constructive interference, as we see here in these diagrams. So this would be complete constructive, this would be complete destructive, looking vertically with wave 1 plus wave 2. This would be not coherent. We would probably get a wave pattern. As you can see, there's a blue wave and green wave, and the red wave here shows the sum of the two waves due to interference. And we can remember what the principle of superposition is. That is the total displacement at a point is the sum of the individual displacements of the waves. In this slide here, I'm going to guide you through an exam question involving the interaction between two waves in a microwave. The diagram here shows the path of the two waves, and they are going to meet at point X. And we are to identify whether this is a microwave oven hotspot or a cold spot. We're told that the wavelength of the microwaves is 12 centimeters. So we'll consider this wave, the one that is going to travel 48 centimeters for the first part of its journey here, wave 1, and we can see it reflects off the surface of the microwave here and travels 19 centimeters before meeting wave 2. Okay, so wave 1 will travel 48 plus 19 centimeters, a total of 67 centimeters. Wave 2 will travel 60 plus 25 centimeters before it meets with wave 1. The difference, or the path difference, is simply the difference between the two distances, and we see that is 18 centimeters. And being that the wavelength of the microwave is 12 centimeters, it's quite easy to see that the path difference of 18 centimeters is 1.5 that of the wavelength of the microwave. So we have this situation here, a path difference of n plus a half lambda, where in this case n is 1. So we can identify this as a point where destructive interference occurs and identify X as a cold spot. CDs and DVDs use destructive interference of light to create a digital signal. The surface of a CD or DVD is covered in pits. That looks something like this microscopically. A laser beam is shone onto the DVD or CD and will get reflected light coming from different parts of the pit. The pit is 1/4 of a wavelength depth. So what would happen at the edge of a pit, we would get let's say two reflected waves, say 1 and 2, one from the top of the pit and one from the bottom of the pit, and these would have a path difference of half a wavelength, one having travelled 1/4 plus another quarter before the other wave had done so. And so the path difference between the reflective waves and is 2 times 1/4 of a wavelength. So the path difference between the reflected waves is half a wavelength. Destructive interference occurs, and so we get a kind of dark spot. And it's a bright and dark spot as the laser beam is passed over the CD that creates the digital signal. On this slide we can see some further diagrams with some numerical detail. This path difference interference is the reason why we see brilliant colours on soap films or oil films. Of course, different colours of light have different wavelengths, and so what occurs is if certain colours experience destructive interference while others experience constructive interference, you'll see the colours where constructive interference is occurring with the reflection of light from the thin soap films or thin oil films.